Okay, so what if I told you that inside every single one of these huge, complex AI models, there's a secret, a smaller, leaner, and way faster version just kind of hiding in there waiting to be found? I know, it sounds a little bit like science fiction, right? But it's actually the core of a totally groundbreaking idea called the lottery ticket hypothesis. So let's dive in and unpack this, because it could literally change how we think about building AI.
But before we get to the really cool solution, we've got to understand the problem it's trying to solve. And believe me, it is a massive problem. For years now, the AI world has been stuck on this issue of scale.
You've probably seen the headlines. The trend in AI has been pretty simple. Bigger is better. We keep building these absolutely gigantic neural networks with billions, sometimes even trillions of connections. And yeah, they can do some incredible things. But this constant push for bigger, 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 well, it comes with a serious price tag.
And this right here, this is the classic dilemma every AI developer faces. On one side, you've got the giant networks. They're super accurate, which is great, but training them costs a fortune, both in time and in raw computing power. And then on the other side, you've got small networks. They're quick, they're cheap, but they usually just can't keep up with the performance of the big guys. It's this constant trade-off.
This brings up this super obvious question, right? If the big networks are so ridiculously expensive, why don't we just build the small, efficient ones from the get-go? I mean, that makes sense. Well, for the longest time, the really frustrating answer has been, it just doesn't work that well. And that leads us to the first attempted fix for this whole mess.
So the industry's first real attempt to solve this was a method called pruning. But as you're about to see, it's an imperfect solution with a really big catch.
Pruning is basically exactly what it sounds like. You take your huge, fully trained network and you start snipping away at it. You look for the weakest, the least important connections, and you just trim them out. Just like a gardener would prune a tree to make it healthier and more efficient.
And right there, that's the predicament. Pruning only works after you've trained the network. So you still have to go through that incredibly slow, incredibly expensive process of training the whole giant model before you can even start to make it smaller. It helps make the model faster later on, but it does absolutely nothing to fix that massive upfront training cost.
So this is where two researchers, Jonathan Frankle and Michael Carbin, stepped in with a completely different way of looking at the problem. They came up with something they called the lottery ticket hypothesis.
Okay, so here's the big idea. The hypothesis suggests that maybe, just maybe, that huge, expensive network isn't actually necessary. That hidden inside of it, from the very beginning, before you've even started training, there is a tiny, perfect little subnetwork that was basically destined for success. And let's look at the original paper for a second. The researchers themselves say that these special little subnetworks, which they call winning tickets, can be trained all by themselves and get just as good as the original giant network. So the secret isn't the size, it's finding this one lucky combination of connections. And that's exactly why they call it the lottery ticket hypothesis. See, when you first create a neural network, all of its connections are given random starting values, or weights. It's kind of like a blind guess. The theory is that just by pure dumb luck, some of those connections get the perfect combination of starting values. They've basically won the initialization lottery, which means they are perfectly primed to learn from the get-go.
Okay, so if these magical winning tickets actually exist, how in the world do you find them? Well, the researchers came up with a really clever three-step method to uncover them.
Here's how it works. First, you do the normal, expensive thing. You train the whole big network. Then, step 2, you prune it, just like we talked about before, getting rid of all the useless connections, the losing tickets. But here comes the absolute genius move in step 3. You take the leftover skeleton of connections, your winning ticket, and you rewind its weights all the way back to the random values they had at the very beginning, before any training ever happened. So now you have this winning ticket subnetwork, right? And it has its original lucky initialization. So what you can do is train just that small network all by itself from scratch. And this is where the results get absolutely mind-blowing.
Get this, the winning tickets they found were consistently just 10 to 20% of the size of the original network. I mean, stop and think about that for a second. That is an enormous reduction. We're talking a potential 80 to 90% drop in the number of connections you actually need.
And this chart just illustrates the most stunning part. You'd think a smaller network would have to be less accurate, right? But look at this. The tiny winning ticket subnetwork doesn't just match the accuracy of the original massive network. In some cases, it even beats it. All that performance with just a fraction of the size. It's wild.
So let's just recap the payoff here. These winning tickets are tiny. They get the same or even better accuracy, and they often train faster, all because they were, for lack of a better term, born lucky. Now, this isn't just about saving money on cloud computing. This could unlock powerful AI for everyone. Imagine sophisticated models running right on your phone or in your car without needing a constant connection to some giant server. The key to that future might have been hiding inside these networks all along.
At the end of the day, the lottery ticket hypothesis completely challenges that bigger is always better idea in AI. It suggests a future where we can build hyper-efficient, powerful networks right from the start. And it leaves us with this one really fascinating question to chew on. If every big AI has a little winning ticket hidden inside it, what other incredible shortcuts and efficiencies are we still completely missing?